In this video, we're going to talk about inflection points. And so an inflection point is basically a point where a graph changes its concavity. So this is the graph that we saw earlier, and we saw that this was concave up because, these tangent lines here were increasing, right? And then up here, they're decreasing, right? So there must be some point here where this graph goes from being concave up to concave down. And that point, wherever it is, maybe right about there, is going to be the point where this graph is increasing, where these slopes are increasing to its steepest point, and then they start going back down. Okay, and so it's kind of like the steepest point on the graph. So inflection point. One thing is at that inflection point, they say that the tangent line actually passes through the graph at the inflection point. So like these points, it's going to probably pass through the graph somewhere else. Maybe way down here. Maybe right here it'll pass through over here. But at that inflection point, it actually passes through the graph. Okay? But a good way to think about this here is that the first derivative is increasing, and then that first derivative is decreasing. So if I were to draw a graph of the first derivative here, these are almost zero, increasing to a maximum point, right? And then they start decreasing again. So this would be kind of like y equals f prime of x. And this actually would probably look more like a normal curve. But the point here is that the inflection point here is like a relative, in this case, a relative max. Right? This is a relative max of the function. It could also be a relative min if it were like concave down and then changing to concave up. So concave down to concave up, you would have this relative min. Okay? So that inflection point here is actually a critical point of the derivative. Okay? So, we could write this: inflection points occur at the critical points of the first derivative. Okay, so now let's think back. So the reason for this, the inflection points occur at the critical point of the first derivative, is that the inflection point is a relative min or max. Let me write that up here. Inflection points are the relative min or max of the first derivative. So if we think back to the critical points and the relative min and max of the original function, okay, so if a function has a relative min or max, then that occurs at a critical point. Okay, but just because a function has a critical point doesn't mean that is a relative min or a max. So that's why we have the first derivative test and the second derivative test, because it could be that the function is increasing and goes to 0, and that 0 is a critical point, but then it starts increasing again, right? And if the first derivative does something like that, then it means that's not an inflection point of the original function. If the first derivative here has a critical point, but that critical point is not a relative min or max of the first derivative, then that critical point of the first derivative is not an inflection point of the original function. Okay? So inflection points occur because it occurs at a relative min or max of the first derivative. Okay? So they're going to occur at the critical points of the first derivative. So, but we could say, but not all critical points of the first derivative are inflection points. Okay? And so what you have to do is you would have to do like a first derivative test, sort of a first derivative test on that first derivative where the second derivative is the first derivative of the first derivative. Okay, so now it's just a whole bunch of words here. So basically here, the inflection points occur, the inflection points are the relative min or max of a first derivative. And so they're going to occur at the critical points of the first derivative, which are not necessarily the critical points of the original function. That's important to keep in mind too. Okay, the first derivative is going to have critical points of its own. Okay, and when you find those critical points, they may or may not be inflection points. Okay, and so what you would have to do is you would have to go and investigate to make sure those critical points are indeed relative min or max of the first derivative, and you would use something like a first derivative test. But when you start using language and calling it first derivative test, then it can get real confusing, right? But you know what I mean. That's the idea. Okay, so what I want to do is I want to first start out here by considering the impossible inflection points at x equals 0 for the following functions. Okay, so now, and this is another good point. I didn't say this, but the critical points, remember, are not just where a function, the derivative of a function is equal to 0, but also where the derivative of a function is undefined. Okay, so let's look at this then. This says consider the possible inflection points. So each of these will have a possible inflection point at x equals 0. Okay. And so consider those and see if maybe they are an inflection point. So here's what I mean by these. I got like 3 examples here, and they're all fractional exponents. So taking the first derivative, I get 5/3 x, and then when I subtract 3/3, I get x to the 2/3. Okay. And then I take the second derivative here and bring that down, and I get 10/9 x to the -1/3. Okay, so now when you look at this, let me actually rewrite this as, this would be like 10/9 to the cubed root of x. And so you can see that at 0, this is undefined. So, and this is double prime, sorry. F double prime of x, or of 0, F double prime of 0 is undefined. And so it's a critical point. We could say, and so it is a critical point of f prime of x. Okay, and so now what you could do is you would make like a table here, and you would have like 0 or -infinity to 0, and then 0 to infinity, and this would be where x is equal to 0. And then you could see here with negative values, when you take the cubed root of a negative number here, then you're going to get a negative value here. And then when you take a cubed root of a positive number, this whole thing will be positive. And so this is going from negative to positive, and so it's a relative min of f prime of x. And so it is an inflection point of f of x. Ooh. Okay, so that's the idea. And so basically then the graph will change concavity at that point. And so let's graph this and see. X to the oh, and by the way, when I bring down the 1/3, this should have been oh no, 2/3. Okay, that's okay. That's right. If I would take another one, then it would be negative. Okay, so let's do 5/3. Okay, and then let's graph this in a standard window. And so we see that at 0, if this thing is changing, it's kind of concave up here and then concave down. So this being concave down, the first derivative is decreasing, and then the first derivative is increasing, and it changes its concavity at this point. Okay, so that's the idea there. So now let's look at this one here. So now I'm going to take the first derivative, and I get 1/3 x to the negative 2 2/3. Okay, so that's the first derivative, and then the second derivative. Oh, and by the way, I made a mistake. I was plugging down here, I was plugging these into the second derivative. I should have been plugging them into this derivative, but in this case it wouldn't have mattered. You would have still got negative and positive, so it turned out right. But I should have been, you got to plug these into the first derivative because you're doing the first derivative test on the first derivative using the second derivative as the first derivative. So I actually plugged them into the wrong place. You're plugging them into here. Okay, so I plugged a negative value into there and I get negative, plugged a positive value. But actually, this would have squared them. A negative value would have given me... oh no, I did it right. I did it right. Darn it. Sorry. I actually did it right because you do plug them into here, not into here. You do plug them into here because you plug to do the first derivative test, you plug it into the derivative here, and this is the derivative we're using to test it for this function. Okay, forget it. I'm confusing myself. Okay, so let me just continue here. So I did that right. I did it right. Okay, but see, these are the things that happen if you're not like a brilliant genius that you can keep track of all these things, and I'm not. I have to really concentrate. Then yes, there's a lot to keep in your mind here. Okay, and so yeah, so it's easy to confuse yourself. But those are the kinds of things you need to sort through. So it's good that this is in the video because you can see that what happens and that's normal if it happens. Okay. So now that's the first derivative. So the second derivative, I'm bringing down a negative exponent here. So I get negative 2/9 x, and then I subtract 3/3. So this is negative 5/3. Okay. So this derivative would be like negative 2/9, and then you would have like the cubed root of x to the 5th. Okay, there we go. It would be like that, and you'd have that negative out front. And so you do have a critical point here. F of double prime is undefined here, and so it's a critical point. So same here. Okay, so you got a critical point. Now let's test to see if it's a inflection point. So we do negative infinity to 0. Oops. 0 to infinity. Okay, and we'll test a negative value. So if I put in a negative value here, the 5th here, it'll keep it negative, and then you can take the cubed root of a negative number is fine, and it's negative. And so this means you'll have a negative over a negative, which makes this positive. And then when you put in a positive value, this thing will all be positive, and you'll have a negative 2 over a positive. And so negative 2 over a positive makes that negative. So this is like the first derivative. So this is like f prime of x. And so the first derivative is increasing here, and then it's decreasing after 0. Forget that. That makes it confusing. And so 0 is a relative min of the first derivative, or relative max of the first derivative. Okay, and so again, it's an inflection point. It is an inflection point of the original function. Or of f of x. Okay, so let's look at this last one and see why this is going to be a little bit different. So now I'm going to take the first derivative, and I get 2/3 x to the negative 1/3. And now I'm going to take the second derivative, and I'm going to get negative 2/9, negative 2/9 times x to the negative 4/3. Okay, so I could rewrite this negative 2/9, and then this whole thing is like the cubed root of x to the 4th. That's what this would look like. So you have a negative 2 on top. Okay, so now, again, same. I'll do same here. That it's undefined at 0. So that's a critical point. So let's make our table. And so what happens here now is I can put in a negative number here, but the 4th power makes it positive, and then you're going to take the cubed root of that, which is positive, so this is going to be negative because of the negative 2/9. Okay, so this is negative, and then if I put in a positive number here, again, this will be positive on bottom and negative, so it's negative. So this thing is like negative here. The second derivative is negative. It's like concave down, but then it's still concave down. It's not changing its concavity. Okay? Neither, we can say f prime x, neither, let me actually, f prime of x has neither min or max at x equals c, or x equals 0, and so x equals 0 is not an inflection point. And what that means is the function does not change its concavity there. So let's graph it. You know what? I didn't graph this one. So let me graph this one first. Well, I'll go ahead and do the one we just did. Let me graph that one. So if I do this x to the 2/3, and then if I graph it, here you can see it's coming down, and it's going to go to 0 and make a sharp, it has a sharp cusp. It kind of takes a turn here, a sharp point. And so notice it's concave down and concave down. That shows up on our table here. Concave down and concave down. It does not change its concavity. It does not have an inflection point. So 0 is a critical point of the first derivative, but not an inflection point because the first derivative does not have a relative min or max. Okay, and then this one here, we're gonna do this 1 to the 1/3. So this is just the cubed root of f of x, and it looks like this. Okay, and it does indeed change. So let me actually I'll go from like -3 to 3 to make it a little clearer. Okay, so so it does change. It is concave up here, so that's a positive, and then it's concave down on the other side. And that's a negative, and it changes its concavity right here. But notice at the point that it changes its concavity, it's a vertical tangent line. And the reason for that is the first derivative is undefined at that point. It's a vertical tangent. Here the first derivative is defined, and yet a horizontal tangent. Here it's undefined. But it's still a critical point, and indeed it changes its concavity there, and it goes from concave down to concave up. Okay? And so that was a critical point and an inflection point. So, the point of all this are the inflection point is where a graph changes its concavity. It is a relative min or max of the first derivative. And so if it occurs, it's going to occur at a critical point of the first derivative. So that means where either the first derivative is equal to 0 or is undefined. All three of these examples it was undefined. But still a critical point. And so you got to do something like this first derivative test to look to see if the concavity is changing, if the sign of the second derivative is changing. So what I said, let me back up because I'm not sure if what I said was correct. What I meant to say is that you do have to set up a table for the critical point and make sure that it is a relative min or max. So performing like a first derivative test on the first derivative, using the second derivative as the first derivative. That's the best way I know how to say it, and checking to see if if that first derivative does indeed go from increasing to decreasing or decreasing to increasing. And if it doesn't, then it is a critical point that's not an inflection point. Okay? So in the next video, what we'll do is we'll actually find the relative min. For a couple functions, we'll find the relative min and max of the function, and then we'll find any inflection points as well. And so we'll do that next.